Okay, I'm sure you listened to the video about Chebyshev inequality, part 1. Now we'll go one step further. This is taking it, the same idea, just developing it a little bit further. It's telling us certain limits of how much you can, how the distribution can be away from a certain point. Here is how we start the subject. We are giving you a variance of a distribution, and we wish to know, according to that information, how much can be away far off a certain point. So again, let's try to get this in a picture form. This is how we start. You have here a point that's called 6D. We also know the variance of this distribution actually I shouldn't use the word variance here. I'm going to use something else. Here. We take a point 6D and we're telling you e x minus 6D squared is equal to 12. First of all, what does this mean, this gibberish that I'm talking here? It means if you take all the x values that are associated with this distribution, it might be 50, 40, 30, 70, 80, it might be like 10 different points, each one with different probability. Obviously they must add up to 100%. You take all these points, you subtract 60, you take the result, you square it, and then you multiply it by the probability of that point of x. You would get 12. Imagine that's the fact. So I'm telling you this fact about this distribution. You take all the points, x can be 50, 55. You just subtract it. 50 minus 60 is 10. 10 squared is 100. And let's assume we get only 5% of that. So it's 5%, because we have only 5%. Sorry, only 5% of x being 50. So we take each random variable and we know the probability associated to that. First we take the random variable, we see how far it's off 60, we square that number, then we multiply it by the probability of that point. And it adds up to 12, only to 12. You can just using intuition, you can see that if these x's are quite close by to 60, because if not the number will be higher than 12. Let's just take an imagination. Let's say we have a number that's 57. So 57 minus 60 is 3. And let's assume that the number associated with 57 is 40%. So what we do is we make 57 minus 60, that's 3. 3 squared is 9. 9 times 40% is 3.6. So you just fool around a little bit here and there, till we get 12. You can just do it yourself, just make up numbers and try to fit in this fact. You cannot go too far, I'm telling you, you cannot go too far off 60. If you go too far, you get a high number. For example, if you go 45, 45 minus 60 is 15. 15 squared is 225. So if you go too far off, 225 is way above 12. So how in the world will you squash that 225 and it shouldn't exceed the number 12? You could do it. You know how? Very simple. You squash it. It's 12 divided by 225. It's 0.0533. If you take only 5% and you let him be so far left by number 45, so even if you take the 45 minus 60, that's 15, you'll square it, you get 225, you multiply it by 12 divided by 225, that is 0.0533, you get the number 12. So I'm hinting you something here again. The same idea I said in the last video. The idea is basically you want to go far left or far right away from 60, no problem. But the further you go, the less you can give him. Because if you go far out and you take the difference from that number to 60 and you square it, it gets a huge number. The number is huge, you can only give him a tiny amount of a portion of a size. He shouldn't blow you up. So you can only give him 0.0533. So here we're giving a suggestion. This is the idea again of the inequality, to put it in precise language. How much is the same question like above. I'm giving you information. I'm telling you this fact. X minus 60 squared is equal to 12. E of x minus 60 squared is equal to 12. If you add together or you take all these x points, I'm not telling you where the x's are. I'm not giving you that information. It might be by 50, by 40, by 30, by 20, by 10, by 70, by 60, by... I'm not telling you where the points are, and I'm not telling you how much percent each point is. So you know very, very little. But you do know that this whole Mishka Babel here, this whole Pachka, is equal to 12. That's what you do know. So you think to yourself, hey, that tells me some tiny amount of information. It tells us that you cannot be too radical here. You cannot be too extreme, going too far off the number 60. And if you do go far off 60, you have to squash them extremely low. So this is just the concept. Now let's formalize it into mathematical language. We'll say like this. We'll take a number, I'll give you a number, and you will tell me how much we have to squash it. So let's go 10. 10 digits away from 60. I wish to put some of my distribution on like the points that are 10 away from 60. That means either by 70 or by 50. They're both 10 away from 60. I want to be radical. I want to put them away from 60. I know I'm going to run into trouble, but I say, you know what? I'll give them very tiny portions. So let's see. How tiny the portion must be. I shouldn't get into trouble. I'm giving you. I want to know how much can I appropriate, apportionate for these guys. I want to put a nice amount of the distribution, a nice percent of the distribution away on the areas that are 70 and above or 50 and below. That's 10 away from 60. So let's start to think like this. Imagine I would put 50%. Just let's do trial and error to get a concept. Imagine I would put 50% of the distribution in this area. 50% will be the far right field and the far left field. So you realize what we will do here is we'll take the 10 squared, that's x minus, the x's here are 70 and above, so it can be even more than that, but because it's 70 and above, but let's make it even just 70. So we get 70 and above and 50 and below. They should take up 50% of the distribution. So that's, you do x minus 60, that is 10 squared, 100, 50% of that. 50% of 100 is 50. So this is way, way bad. We have a number 12 here. How in the world can we be so generous and give for 70 and above and 50 and below, you see that curved line, and give them an area of 50% of the distribution? You'll run into big trouble. If you do that, it's impossible that this equation should be true, that x minus 60 squared should be 12. It will be at least 50. At least 50. Because imagine we have 50% just exactly 10 units away. We already have ten squared is 100, and 100 is 50% is just 50. So how can we handle that? It's a catastrophe. How about we say, okay, we are just going to place, I can jump from 50% to 20%. That sounds much more moderate. I'm only going to put 20% of the info, of the data, in the radical. Let's call them the radical sides. That means 10 away from 60. It means either 50 and less or 70 and above. So then we do this 10 squared. It's actually more than 10 squared because some of them are even below 50 or above 70. But to be conservative, let's say we put them all, they should just touch the point of 50 and 70. And we will right now be moderate. Only 20% of the data goes at these points. So we get 100 times 20% is 20. No good. We only allow you to have this, as you see, ex minus 60 squared is 12. You cannot do that. You get it to a high number. Let's give it a try again. 10%. Oh, now we're okay. Now we're okay. What do we do now? We say we are going to place 10% on this extreme zone. So again, we do the we get them there. We do the, since they're 10 away from 60, so we have 10 squared, and we have only 10%, so it's 10% of 100 is 10. Okay, now we get the number 10. Not bad. It's less than 12. So the rest we can, if you wish, you just imagine that you put some of them even more to the right and the left to up you. We say that 10% of the data is on these two extremes, and the other 90% is actually also contributing something to this variance. So obviously they're also going to tilt something. So let's put them wherever you want. I guess you put them in the middle. You can put them you just figure it out in such a way that they should make up another 2 units. You don't need to work too hard for that. That is at least sensible. Very far-fetched, but sensible, that 10% of this shall be 10 units away. Like this, we get a number that's less than 12. And for the other, to make up the 12, we have the other 90% that we can put them in the middle, or you want, you put some of them in the far right, far left, and the rest in the middle. You just fool around with it, you get the number 12. What is the moral of the story? How do we know the exact, again like we said in the last video, the exact number of how much percent you can put outside 10 away from this thing? Answer is, it's 10 squared times something is equal to 12. Ten squared times x, is the percent you can put outside, is equal to 12. You solve for x is equal to 12 over 10 squared. That's 12 hundredths. You can put 12 hundredths of the distribution outside 10 away from the 60 zone, in the radical zone. You can put, that's how much you can put. You can put 12 over 10 squared, that is 12%. If you do that, and everything else is exactly at the point of 60, so that doesn't cost you anything, it just makes it 60 minus 60 is 0, doesn't change the variance, a drop. But it's not variance, whatever this kind of calculation, it's on the point of 60. So we have 88% on the line of 60. 88% is there. That just doesn't tilt it anyway. 12% is on the radical points, respectively 50 and 70, you know what will happen? Then we get this miracle. Then we have the 10 squared, that's 100, times 12% is 12. We get the variance of 12. So this is at the best case, the best case possible. Don't be fooled, this will never happen, but at least the point of this is that it's impossible in the real sense to have even a drop more than 12% in the radical zone. I call it the radical zone. If you are given the information that ex minus 60 squared is equal to 12. This is the information that you start building the building. If you know this information, then you're asking to yourself, how much percent can I have in the radical zone? It means 10 away. Answer is, it's 12 over 10 squared. Now, the next video, I'll just continue to take it one step further, and it'll just be so simple that you'll think to yourself, like, why do you need some big genius for this? Why do you need Chebenshevs, whatever the name is there? It's just childish. But that's what math is all about. You take simple things and you just reveal it, and you see the wisdom of God. Thank you for listening.